All right, everybody, welcome back. In this video, we're going to discuss information from Unit 2, Section 8 of AP Calculus, the product rule. And we kind of start here by, tying back to what we talked about 2 sections ago in Section 6, some of our basic, algebraic derivative rules. A lot of times in mathematics, when we try to come up with rules for how things work, they indeed do work exactly the way that we would want them to work. Like, the constant multiple rule for derivatives. If we take the derivative of a constant times a function, the result is just the constant times the derivative of that function. That's exactly what we'd want. The sum rule, if we take the derivative of two things being added together, well, hey, cool. We would want it to be the derivative of the first thing plus the derivative of the second thing. And the difference rule, we would want that to be the derivative of the first thing minus the second thing. Wouldn't it be nice? I feel like I need to play like a little Beach Boys clip there. Wouldn't it be nice if when we took the derivative of the product of two functions, it worked the way that we wanted it to? And it would simply be the product of their individual derivatives. Wouldn't it be great if the derivative of f of x times g of x was equal to f prime of x times g prime of x? That would be awesome. It would be easy for us to remember. It would be easy for us to use. It would be exactly what we want. Unfortunately, that's not the case. And we can kind of show that with a very simple example. If we imagine taking the derivative of x to the fifth, we know we can get that using the power rule, and the derivative of that's 5x to the fourth. But we can split up x to the fifth is x cubed times x squared, and if we try to take the derivative of that, we should end up with 5x to the fourth. But if we try and use this, simple but incorrect product rule, the derivative of x cubed is 3x squared, the derivative of x squared is 2x, the product of those is 6x to the third, which is not the same as we get using the power rule when we take the derivative of x to the fifth. And so that shows us that the product rule is not one of these nice, neat rules where it is exactly what we would have expected. It's unfortunate, but it's reality. So our next task is going to be, well, let's go ahead and figure out what the product rule is. So what is the derivative of f of x times g of x? And so we're going to take the derivative of f of x times g of x, and we're going to go ahead and, much like we did with all of these other basic algebraic rules, we're going to set it up as the limit of a difference quotient. This derivative is equal to the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, because our function here is f of x times g of x, and so we're taking the function at x plus h minus the function at x all over h. And we're going to take the limit as this approaches 0. Now, unfortunately, if we look at this, there's not really any algebraic simplification that we can do from here. So we need to get a little bit creative, a little bit tricky in the way that we do things here. And we're going to use a technique that you'll see a lot as you get into higher mathematics courses, improving things. A great technique that we can use in some of our developments and proofs. There are two really great techniques that we can use. Multiplying whatever we have by 1, which, depending on the form of 1 we use, can simplify things into something that we can work with. We saw this with limits when we were, rationalizing a denominator, for instance. We would multiply by 1 in order to simplify. Another thing that we can do from a simplification standpoint is we can add 0, where the form of 0 that we add is what makes this truly interesting. Okay, and so I'm going to go ahead and add 0. And when I add 0, I'm going to do it like this. I'm going to keep this first term of my limit, and the last term I'm going to move all the way over here at the end. and then I'm going to add 0. And the way I'm going to do that is I'm going to add something, and I'm also going to add its opposite into this expression. And the way that I build this, I really have two options. What I want to do is I want to take one factor from each of these terms. For instance, if I take f of x plus h from this term, then I want to take g of x from the other term. If I take g of x plus h from this term, then I want to take f of x from this other term. But I'm going to add in these terms that contain one factor from the first term and one factor from the last term, where it represents both f and g. So I have two options here. I'm going to choose to do f of x plus h, g of x. So I'm going to subtract that away, and I'm also going to add that expression in. And by doing that, I haven't changed the value of the original at all. And now I can proceed onward from here. By splitting these into two limits, what I'm going to do is I'm going to go ahead and I'm going to group these two terms together as one limit, and I'm going to group these two terms together as another limit. Both of those limits have h as their denominator, and so this is going to be equal to the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x plus h, g of x, all over h, plus limit as h goes to 0 of f of x plus h, g of x, minus f of x, g of x, all over h. And now in both of these limits, I can go ahead and factor out a common factor in my numerator. And in the first one, I can factor out f of x plus h from both terms. And in the second one, I can factor out g of x from both terms. And now I'm going to use another one of my limit properties. I'm going to use the product property of limits. Namely, I can split each of these limits into the product of two things that are equivalent to that limit. So I'm going to go ahead and split this into the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x. If you're really paying attention, you can kind of see what's going to happen here. And then I'm going to split this one up into the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're almost finished. Okay, we're going to take all of these limits now. The limit as h goes to 0 of f of x plus h, I just substitute 0 in there, and it's equal to f of x. This limit right here, you should recognize as the definition of the derivative of g. So that's just equal to g prime of x. The limit as h approaches 0 of g of x, well, there's not even an h in there. That's just going to be g of x. And then I look at this limit right here, and you should recognize that that is just the definition of the derivative of f of x, or f prime of x. And so we've just shown that the derivative of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. All right, that is our product rule. I'm just going to keep rolling. And you see it at the top of the next page here. For two differentiable functions, f of x and g of x, their product is differentiable, and the derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. So first function times derivative of second plus second function times derivative of first. And of course, addition is a commutative property, so it's also okay if you think about it this way. That's also a way of thinking about the product rule. So let's go ahead and let's take a look at this first example. We're going to go ahead and do part A and B here. First, we're going to find the derivative of the quantity 3x minus 5 times 2x squared plus 8 with the product rule, and then we're going to find it without the product rule. All right, so y prime is equal to the first function times the derivative of the second. The derivative of 2x squared plus 8 is just going to be 4x plus the second function times the derivative of the first. And I'm going to go ahead and simplify this. I might as well. This is going to be 12x squared minus 20x plus 6x squared plus 24. And if I combine all of that, I get 18x squared minus 20x plus 24. If you're feeling ambitious and you want to do a little bit of extra algebra, there is a common factor. You could factor out a 2 from everything there, but I'm not really going to bother doing that. Let's just stay there with y prime equals 18x squared minus 20x plus 24. Now, 2 sections ago, we could do problems like this without the product rule, but in order to do that, the first thing we had to do is we had to go ahead and multiply this out. So we would multiply this out. We've got 6x cubed plus 24x minus 10x squared minus 40. Okay, so putting that in standard form gives us this. Oops. And now I can just go ahead and use the power rule. So dy dx is equal to, I wanted to change up my y prime and my dy dx there, but we can just go ahead and use the power rule to take the derivative of each of these individual terms. And bada boom, bada bing, we get the same derivative. More proof for us that the product rule is, true. All right, I think we're going to try and get through a couple more of these product rule examples here before we call it a day on this video. So let's go ahead. In part C, we've got y equals x to the negative second times the cosine of x. So we're going to go ahead and use the product rule. First function times the derivative of the second plus second function times the derivative of the first. And so dy dx is equal to negative x to the negative 2 sine of x minus 2x to the negative 3 cosine of x. And then we could factor. I'm going to factor out a negative x to the negative 3 here. And that leaves us with x times the sine of x plus 2 cosine of x. That's a nice looking derivative for this function. Could also write that with the x to the negative third, make that a positive and move it into the denominator, write it as a fraction. All right, one more. Dy dx is equal to first function times the derivative of the second. The derivative of the natural log is 1 over x plus natural log times the derivative of the first function, which is 3x squared. Simplifying gives me x squared plus 3x squared natural log of x. I can factor an x squared out of both of those, so I'm going to go ahead and do that. And there's my derivative. All right, we're just about out of time for what I can record, so let's call it quits here. You can come back and join me for video 2 in this section, and have a great rest of your day. See you next time.